Okay, great day to you. And we're going to do some t-test computation here. And I'm going to go pretty slow. So some of this you may want to listen to it 2 times or sit and dwell on some. But let's get going. And I'm going to do this, I think, in 2 parts. The first part I'm going to do as the computation. And the second part I'm going to do the t-test as you consult the t-table. So how to use a t-table. That way it'll at least make it shorter and not kill you with boredom. All right, so let's get moving here. So the next thing I want to draw your attention to before we get too much into this is that for homework 3 here on the week 4 module, you are going to probably want to download the independent t-test formulas. And this is a way in which you can walk through this work that we're about to do and have a couple different ways to try and get it into your brain. And so let me move into the bulk of our work here for t-test computation. All right, so starting out, here is the formula for the t-test. And in this formula, I'm going to point out a few of the features here. So you have T, OBT. OBT stands for obtained, so the t-score that was obtained. And the M1 and the M2, the M1, as you can see down here, it's the group with the higher mean. M2 is the group with the lower mean. And they can be used interchangeably here. And the reason for that is you do not want a negative t-test. So it doesn't really matter which mean that you put first, because the whole idea is to answer the question, is there a difference between the group? And this difference is going to be based on probability. It's going to be based on using the t distribution, and there you have it. And then so the SDM stands for the standard error of the difference between the means. And so like when you did the z-score formula, if you may remember, this looks a bit like that. The z-score formula was mean 1, or x subtract mean 1, or you could flip them around, divided by the standard deviation. Now this is the standard error of the difference between the means. So when you have 2 means or more, SDM, the standard error of the difference between the means, is a combined standard deviation. Let me say that again. SDM is a combined standard deviation of 2 means. Oh, let me actually go back. I want to show you one other thing related to this. So here you have a basic fraction, I guess you could say. And so when you subtract M1 and M2, you're going to get a number. And then here at the bottom, you're going to have also a number. And this term down here represents error or variance. And the variance could be due to a number of things. It could be due to large differences in the way the population was compiled. We talked earlier about the difference at baseline or at pre-treatment for those who are anxious, and in the anxiety study with cancer. And so this error term, if you there's 2 ways, well, there's really 3 ways in which you can get a higher t, and you want a higher t. You want t being large is good. And so if you take this number here and divide it by this, the smaller this is, or the less variance, the larger this is going to be. all things being equal. Or if this is like a moderate size and this is really large, that'll also make that larger. And so let me introduce you to a couple of the t-test assumptions. And these I have named. If you Google them, you're probably not going to find these, but I just listed them in such a way that you might be able to easily note the differences. Let me take a quick drink here of kombucha. All right, so the first is the sample assumption. So the larger the sample, the less likely the difference is between the two means is created by sampling error. And if you recall, sampling error is tied to making a type 1 error. So large sample sizes have less sampling error than smaller ones. The second thing is the group averages assumption. So t will become larger if the difference between the two means is larger, and the less likely that this is created by sampling error. Sampling error, as you can tell, is what we really want to avoid. And in this particular case, one good thing is to have just natural large differences. Small differences may be there. However, you're going to need to discern what causes the size of the t. And the third thing is the variance assumption or the dispersion assumption. And this is related to what I was just talking about, where you have a standard error or standard deviation that is really small and tight. That means there's just not a lot of error or not a lot of noise. And the less likely that the difference is between the two means created by sampling error. Okay, moving on. So here we go. We're going to start calculating this, and I want to introduce you to what this term here at the bottom is, SDM. So we've talked a little bit about it conceptually, and now we'll look at it mathematically. So SDM is calculated by roughly a 10-step process. And so here we go into this. And if you'll see here that the equation has a number of things in it that you need to know about. First, you have SS1 and SS2. So SS1, or SS, is sum of squares. And if you recall from a couple weeks ago, you calculated the standard deviation based on the deviation method, where you took the deviation score and subtracted it from the mean. And then you squared the deviation score. And then you added up the deviation scores, and so the squared deviations. And so at one point during your homework, in your quest to get to standard deviation, you bypassed or went through the step of getting the sum of squares, or the sum of squared deviations. That's another way to say it. So SS is the sum of squared deviations. And rather than do the deviation method where you are subtracting x from the average and squaring it, I'm going to show you a shortcut here based on a simplified formula. Here you also have n, which n stands for the sample size. So n sub 1, n sub 2. This is the sample size of group 1. And this is the sample size of group 2. And so when you add the two together and subtract 2, this right here is your formula for degrees of freedom for the t-test. So you'll need to know this in the future. So n1 plus n2 minus 2 is the formula for the degrees of freedom. Now, if you think back to the standard deviation, this is very similar to that. So standard deviation, you had sum of squares divided by the sample size, n, minus 1, and then you took the square root of it. So this is just adding another standard deviation to the mix. All right, so the question is, well, how do we get sum of squares? Where do we find it? What's the quick way that I was talking about? And here it is. So this nice formula here, we need to draw your attention to a couple of terms here. Now, this stands for sum of squares, sigma, which means to add together x squared. And then here you have parentheses around sigma x, which is you take the sum of x and then square it, divided by the sample size for the group 1. So this could be SS1. I think that might be how it's listed in the handout. So SS1, and then you have sigma x squared minus the sum total of x squared. Okay, so and then just to highlight that this equation, sum squared 1, will eventually go here, and sum of squares 2 for the second group will go here, and then you will be on your way. All right, so here we go. We're going to start out. I'm going to give you a set of scores here in step 1, and the first thing that you're going to do is place the scores in some kind of frequency table, and this just organizes it for you. And so here we have in group 1, this is also known as M sub 1, you have the individual scores x, 8, 10, 12, 6, and 6. 8, 10, 12, 6, and 6. And what you want to do here is make sure that you have a column for x and then a column for x squared. And you could just do this on paper, pen or pencil. And so step 1 is just organizing. Step 2 is then you square the individual scores. And so here you have x of 8. This is one person got a score of 8. Whatever this means, you square it, you get 64. You do the same with 10 times 10 is 100, 12 times 12 is 144, and so on. All right, now, in the equation, there are two different terms. There is the sum of x squared, and then the sum of x squared. And I know that's confusing. They're very similar. But sum, the sigma, whenever you see this, it means you're adding up the column, or you're adding up the scores. So sigma of these 5 scores is 42. So this is sigma x, and you put it in a parentheses if you want. Okay, and then you have x squared. When you add up all of the squared scores, you have sigma parentheses of x squared. Okay, so and that you get 380. So these add up to 380. All right. So step 4 is to take a look here, and it's just the math. So you have sigma x of 42, which we just talked about. You have sigma x squared, so 42 times 42, and this is the term we're going to be paying attention to. on this side, that gets you your sigma x quantity squared. And 42 times 42, then you square that, and you get 1764. And then over here, you have the sum of x squared, and that's 380. So here are your two terms, sigma x squared, this part, and then sigma x squared. All right, so let's go to the formula for, I think I was pointing to the wrong thing, the wrong screen, sorry about that. So, so here you have the terms sigma x squared. So sigma x squared is 380, and usually you're going to have the smaller of the two numbers be right here. So sigma x squared 380 minus the sum of x in parentheses squared, that's going to be 1764 divided by 5. Okay, so 380 minus 1764 by 5, divided by 5. And you end up getting 27.2. So take a look at this math, how I got there. If you have any questions about this, make sure and bring them to my attention through either an email or the Google Doc or, you know, anything. So now let's put it into the equation. So step 6 is you populate the SDM equation with sum of squares 1. And so sum of squares 1 was 27.2, and you put that in the equation. So here it is. All that work just to get this number. And the good news is you get to do all that work again. So the second time you have sum of squares 2 that we're looking to get. So let's look at that. Here's sum of squares table for group 2. So if you have a problem that says find the t-score for these scores, again, you want to put it in a frequency table. And here's the frequency table for group 2. And you have 9, 7, 8, 5, and 6. And I just went ahead and squared those together with under the column of x squared. And if we go through, you can get the terms here. So you have sigma x is 35, so you add up all of these scores, 35. You then have, whoops, back, no clicking. Okay, you have sigma x squared. You have 35 times 35, or sigma x squared, and the answer is 1225. Here you have sigma x squared, the different, sigma x squared, you get 255. So you're adding up all of these to get the sigma x squared without the parentheses. So you have the with the parentheses one and the without the parentheses one. So this is the without the parentheses one, the sum of the squared scores. All right. So you square first and sum second, and then on this one you sum first and square second. Okay, it's the reverse. And I put that in the handout, so make sure you read over that and look at the handout. All right, and so we calculate it just like we did before. We put in 255 here. We put in the square of the sum of the scores to get 1225, and then here we have your sample size. Next step is, and then so you get the sum of squares for group 2 is 10. So it's smaller than the first one. All right, so here you have it all plugged in. So now you have, sum of squares 1 was 27.2, and in this case, sum of squares 2 is 10. So you're beginning to populate this equation. So next thing we want to do is finish it out by putting the sample size in. And the sample size for this is 5 for group 1, 5 for group 2, subtracted by 2. And then you do the same over here, 5 and 5. All right. And then here it is. So the SDM for the equation is the square root of what we just did. And now this is where a lot of people make errors because they forget the order of operations. So you start with your parentheses, do things within the parentheses first. So let's simplify these. You're going to, first thing you're going to do is you're going to take 27.2 and add 10 to it. And then you're going to solve for the denominator in this particular fraction. And 5 plus 5 minus 2 is 8. So you have 37.2 over 8 divided by 8. And then in this parentheses, you have 1 divided by 5 plus 1 divided by 5, which is 40, 0.40. 0.40. So 1 divided by 5 is 0.2. Add those together. And here it is. You have 37.2 divided by 8, 0.2 plus 0.2. So you then will end up getting, if you divide 37.2 by 8, you will get 4.65. And then add these together and you get 0.2 plus 0.2 is 0.4. And if you remember, when the parentheses are together here, this means that you multiply this term with this term. Okay? And I've just written it a little differently here. So you have this term multiplied by this term. And then, of course, you have the square root of all of that. And you come down to the square root of 1.86, which the final answer then is 1.36. All right, so now we did all of that, and you have gotten the answer for this little set of data. So for the standard deviation, standard error for the difference of the mean, SDM, the answer is 1.36. Now, another thing a lot of people do is they forget to put it back in the equation. So they'll just say, oh, right, we did all that work and now we've got 1.36. Well, we're one step away from being done. Here you put 1.36 in the denominator, and then you still have to include the mean of the first group and the mean of the second. And you know how to take averages, so you just put the average here, 8.4 minus 6.2 divided by 1.36, and your OBT, T obtained, is 1.62. So this is your T score. All right, so what? Determine if TOBT is significant by consulting the t-table in the appendix of Warner. So that is going to be a separate video just because this is a little long, and I'll get that out to you really quick. But there's your t-value. You have it. Now the next thing you do is you take it to the t-table. Okie doke. And that will be coming up next. So stay tuned.